Hi there, I'm Hoda, and I am a new faculty member with joint appointment in the machine learning department and ISR, and I'm looking for PhD students who are broadly interested in the societal aspects of artificial intelligence and machine learning. So in the next 10 minutes, I thought I'd tell you at a super high level about my past and future research projects. If you have any questions, please feel free to email me at this address. So needless to say, artificial intelligence and machine learning are reshaping our society, and this rapid change necessitates a two-way exchange between computer science and social sciences so that we can properly understand and address the societal aspects of artificial intelligence. The primary goal of my research is to examine these issues through an interdisciplinary lens. So today I will focus on a particular ethical and societal concern that comes up frequently in the practice of machine learning, especially when machine learning is utilized to make high-stakes decisions for people in domains such as employment, credit lending, criminal justice, and beyond. The issue that I'm going to talk about is that of unfairness in outcomes that ML-based decisions produce. Now, when I talk about unfairness in this sense, I am referring to inequities in the way the system's decisions distribute some immediate notion of harm or benefit to people who are directly subjected to the decisions made by the system. So this type of unfairness has recently been at the center of several controversies. For example, there was a ProPublica article a while ago titled Machine Bias, which investigated a criminal risk assessment software called Compass, which is widely used to inform sentencing decisions for criminal defendants. The ProPublica article claimed that the Compass tool is biased against Black defendants because the percentage of African-American defendants who are falsely classified as high risk by the tool is much higher than the false positive rates for the white defendants. Interestingly enough, the team who was in charge of designing this tool responded by arguing that, well, equality of false positive rates is not really the right notion of fairness here. We had thought about this issue, but we had formulated fairness in terms of some form of calibration or equality of positive predictive value, to be exact. Now, stories like these have motivated a very active area of research these days, which seeks to quantify and guarantee fairness for machine learning. And this literature, this scholarship at a high level is referred to as fair ML usually. Now, of course, to make a predictive model fair, a model that we train in order to make it fair, the first step is to define fairness rigorously. Various mathematical formulations of fairness have been proposed, and the majority of these definitions focus on group level fairness, requiring that a certain metric that at a high level quantifies some notion of harm or benefit across socially salient groups, this metric should be equal. Second formulation talks about formalizing fairness at the individual level, and at a high level, it requires individuals who are treated similarly to be treated similarly. Now, two remarks here. First of all existing notions formulate fairness as some form of equality, either across groups or individuals. And at least the machine learning side of FairML has mostly revolved around devising algorithmic mechanisms for guaranteeing these notions of fairness. And much of the prior work addresses fairness at the group level. For example, equality of false positive rates is a popular notion of fairness at the group level. Relatively little attention has been devoted to intersectionality and fairness at the individual level. And I will speak briefly to the relationship between fairness at these different levels in one of my papers. So speaking of significant findings in the literature, it has been shown that simultaneously satisfying multiple fairness criteria is impossible. For example, satisfying both of the fairness notions at the heart of the Compass controversy is not a possibility. So with that overview of FairML, let me mention two principal sets of issues that my prior work attempts to address. So the first set of questions that I'm concerned about is about measuring unfairness. And this is assuming that the relevant notion of harm or benefit is already quantified properly and it is given to us. So given a distribution of harm or benefit, how do we summarize it into a scalar corresponding to unfairness of the total unfairness of the predictive model that we have trained. The second set of problems is concerned with formulating fairness. For example, if we define fairness as the equality of some notion of harm or benefit, how do we properly quantify the relevant kind of harm or benefit given the application domain and the context at hand? So let me tell you very briefly about two of my papers that address these two questions respectively. So let's first begin with the question of measurement. So in a paper that appeared in KDD 2018, assuming that we all accept the conception of fairness as some kind of equality, we introduce a less binary, more general formulation of unfairness as inequality. So our core idea was to employ existing measures of inequality from economics to measure the overall individual level unfairness of a classifier in an axiomatic, well-justified manner. Now, importantly, a particular mathematical property of our proposed family of measures allows us to sort of interpolate between individual and group level fairness and gain insight into the tensions between these two forms of unfairness. So let me also very briefly talk about the question of fairness as the equality of what. In another paper, which also appeared in KDD 2019, we took a descriptive approach to this question and tried to answer the following question. Among the existing notions of fairness, among the existing mathematical formulations of fairness, which one best matches people's perception of fairness in a specific decision-making context, let's say one resembling the compass context. Here, we conducted a series of adaptive human subject experiments on Amazon Mechanical Turk by utilizing active learning schemes to provide an answer to this question. Interestingly, we found that there is one very simplistic notion of fairness called statistical parity that seems to be best capturing people's fairness judgments, but that is only among the existing mathematical formulations of fairness. So in a sense, the results that we got showed the limitations of some of these in the existing notions of fairness. So now let me very quickly, let me see how much time I have. So let me very quickly tell you about some of the high-level directions that I'm planning to pursue in the future. So the first direction that I would like to pursue is to design and study effective ways of comparing and combining algorithmic predictions with human judgments in order to get the benefit of both worlds. On the human side of it, there is a lot of insights that we can borrow from behavioral economics and moral psychology. There are even formal models there that we can use. On the machine learning side, there are things like, for example, coming up with reliable confidence intervals and those things, so we can decide when to give the decision to a human, when not. So that's one of the directions that I'm interested in following. So another critical problem is the formal study of various sources of bias. So of course, one major source of bias and unfairness through a model that we train could be that the training data is biased. It reflects past injustices, and as a result, the model, when we train a model on top of that data, of course, the model is going to reflect those biases. But that's really not the only source of unfairness. The unfairness can really creep into this whole pipeline at pretty much every stage of the process. The literature currently lacks a formal understanding of how these distinct sources of unfairness interact with one another and which source of bias each of the proposed algorithmic interventions aim to tackle. Now, one of the main goals that I have for my future research is to come up with a deeper, more theoretical understanding of how these different sources of unfairness contribute to the total unfairness, how they cancel each other out, and based on that, come up with a practical guideline for choosing and designing the right type of algorithmic intervention. So another topic of interest is the study of long-term impact and consequences of automated decisions, for example, how it impacts future generations. In our recent work, for example, we utilized MDPs with continuous state and action spaces to model a society with intergenerational transfers of socioeconomic status and derive the optimal policy for allocating opportunities over time. And here, for example, what we observe is that the optimal policy is very much dependent on the parameters that describe that particular society. And last but not least, the societal implications of ML-based decision-making goes well beyond concerns for outcome unfairness and discrimination. There are concerns that are broader in nature. They fall more under the broader category of procedural justice. To give you some examples of that, GDPR, which some of you might be familiar with, prescribes several rights for decision subjects, which include, but are not limited to, the right to obtain human intervention, to express one's point of view, to obtain a reasonable explanation of the logic involved, and to challenge the decisions. So the key question here is, can we mathematically capture any of these requirements? And can we at least partially automate the process of complying with them, especially given the scale at which these decisions are automated? So if any of these questions sound interesting to you, please feel free to get in touch with me. Thanks a lot for listening and good luck in your doctoral journey.